And I'm going to talk about this mission. I've been working on this mission now for more than 5 years. It's what we call a PI-led mission. That means there's a principal investigator, and that's my friend, Hal Levison. He is at Southwest Research Institute in Boulder, Colorado. And his deputy, my friend, Kathy Olkin, is also at Southwest Research Institute. I'm the project scientist. I'm at Goddard Space Flight Center, usually in Maryland, but right now in Florida because we're getting ready to launch. And our project manager, also at Goddard Space Flight Center, is Danya Douglas Bradshaw. And as I'm sure you know, any kind of large project like this requires hundreds and hundreds of people. We have a large and very dedicated team. And the fact that we have been able to get this mission ready to launch on time during COVID is a testament to what a great team we have had. And it's just been a pleasure to do every step of this mission. So what is Lucy? Well, first of all, it's named, it's not an acronym. Usually NASA loves acronyms, but this is just a name. And we took the name from the Lucy fossil. This is a human ancestor fossil that was found in Ethiopia in 1974 by Donald Johanson. And it represents our hopes for the Lucy mission. We are hoping that these asteroids that we are going to visit will be like a fossil in that they will tell us about what the very earliest solar system was like. And I will try to explain why we think that and how we're going to try to test that with the Lucy mission. So when you studied the solar system in school, you would probably look at a diagram like this of the planets going around the sun. The sun is in the center of those concentric circles, and then we have working outwards Mercury shown as a white circle, and then Venus is yellow, Earth is the blue circle. Then there's Mars. You probably saw the asteroid belt in between Mars and Jupiter, which is the outermost planet that we're showing here. And then outside that, there's more planets, but we're zoomed in so we don't see them. But you probably did not see this other group of asteroids that the two arrows are pointing to that are colored that sort of tan color. These are the Trojan asteroids. And they're there because there's kind of a balance between the gravity of the sun, which is the strongest influence on anything in the solar system. But Jupiter balances objects in these locations so that if they start out there, they tend to stay there. The other thing you might notice from this is that even though they're called Jupiter Trojans because they're balanced by Jupiter's gravity, they're not really very close to Jupiter. And in fact, the Lucy spacecraft will be closest to Jupiter when it's near the Earth and not when it's in the Trojan asteroids. So our mission, we call it a tour because we are not going to just one asteroid. And in fact, we are going to 8 total asteroids. 7 of them are in the Trojans. One of them is a main belt asteroid that we are going to use as a practice target on the way out. We're about to launch in a little bit more than a week. We go around the Earth a few times and we get to our first target in 2025. And I'll show you the full trajectory of Lucy in a little bit more detail as we come up. And then in the lower right there is just a cartoon version of our spacecraft, but we'll show you some better pictures of what it looks like as well. So, well, let's see. This is just showing the Trojans and the Earth going around. So here's what we think about when we think about calling the Trojans fossils. If you look on the right side, what you see is what we think the very early solar system looked like. We know that stars, like the sun, formed from clouds of interstellar gas and dust that collapse from gravity. And because they're rotating, they flatten into a disk. At the center, the star forms. But in the disk, you also get material clumping together. And this builds up into what we call planetesimals, but you could also call asteroids. And these are more or less the building blocks for all the planets. But as you get further away from the sun, the temperatures are lower, so the composition of those building blocks changes. And in particular, once you get far enough away, things that are gases in the inner part of the solar system are solid. So water ice, for example, starts freezing once you get to about the distance of Jupiter and beyond. And so we think that this has a role to play in how the planets are built. But getting this material to study is not very easy because most of it got scattered away after the planets were formed. Some of it is in the Kuiper Belt, a newly discovered, new meaning in the last 20 years, belt of asteroid-type bodies out past the orbit of Neptune. Pluto is one of these, one of the largest. And you may recall the whole, is Pluto a planet controversy? It's because we discovered this whole belt of objects of which Pluto is just a part. So those are where a lot of this material ended up, but some of it got scattered inward and got trapped in these special spots that are called Lagrange points. And they're much easier to get to. So that's why Lucy wants to go to the Trojans. One of the clues to why we think that these weren't formed in the Trojans but came from somewhere else is that when we look at them from the Earth with telescopes, we see that they're not all the same. And if they all formed in the same place from the same material, the same distance from the sun, it's hard to explain why they would turn out to be different. They differ in their colors and some other properties, how much light they reflect and so on. And so that's a clue that they must have formed somewhere else. And that's part of the reason that we want to explore them. The other part of it is that we now have really detailed computer models that can simulate the early solar system. And they show the same thing, that the giant planets form closer into the sun and they move around and they scatter all of the small remaining planetesimals, and some of them get captured in these locations. So it's pretty exciting because this kind of material does not exist in the main belt asteroids. And it also doesn't come to the Earth as meteorites. So we don't have samples of this kind of material. Well, here's the targets that we're going to go to. A couple of them had names. We gave names to the rest, and we followed the tradition of naming them for characters from the Trojan War epics. So you can see here the sizes of them compared to my home state of Delaware. So I'll talk a little bit about them. Euripides is an interesting one because we know that it was involved in a really large collision. We know that because we can see the fragments of that collision, many other smaller asteroids that have very similar orbits. And in fact, we found a satellite orbiting around Euripides with Hubble just a couple of years ago. And that's another thing that you would expect from something that's been in one of these large collisions. Just a note about the names, the satellite of Euripides is named Keta, and that's a first. It's named for an Olympic athlete. We started this new naming convention because we're running out of names from the Iliad, even though Homer liked to make very long lists of names. we are running out of them. There are more Trojans than we can name. So smaller Trojans will now be named or can be named for Olympic athletes. And this particular object is named for Enriqueta Basilio, who was a track athlete for Mexico in the 1968 Olympics. But more importantly, she was the very first woman to light the Olympic torch at an Olympic Games. So we thought that was quite an appropriate reason to name it this way. And she has a connection to Euripides because Euripides was a herald in the Iliad, and the herald's job was to carry a staff and go over to the enemy lines and carry messages back and forth. And the Olympic torch relay that starts every Olympic is modeled on this original activity of heralds. So we liked it for that reason. The other one that we have several more. Lucas is one of the slowest rotating asteroids in the solar system. Orus is about the same size as Euripides, but it's a different color. So that's a perfect comparison to make. Why are they different in this way and similar in other ways? And Patroclus and Menecius are a binary pair. That means they orbit each other. And because they're about the same size, they're actually orbiting a point in space that's between the two of them. And these are fairly common in the outer part of the solar system in the Kuiper belt that I was talking about before, but we don't see very many of them in the Trojans. So we think this one may be a particularly pristine remnant of this original chaotic era of the solar system. All right, the next few slides, I'll show you the trajectory. So after we launch in a week, we go around the Earth. We go around a couple of times with a couple of close flybys of the Earth to boost our orbit. And we finally get out to our first Trojan target in 2027. So a little bit less than 6 years after we launch, we'll be getting our first encounter with a Trojan, and that's Euripides and its satellite Keta. And just a month after that, we go by Polymele. So even though these are spaced pretty far apart in terms of their distance, it's not like in Star Wars where the spaceship's always dodging through all these very close together asteroids. This is a very close separation, just a month. We're traveling 3 to 5 miles per second, so you can work out how far that is. It's not that close, but for us and all the things that we have to do with the spacecraft, that is a very short amount of time. Polymele is our smallest target, so we actually fly a little closer to it than the others. Most of our targets we fly past at 600 miles above the surface. For Polymele, we're flying by at just 270 miles above the surface. And it's important to say that we don't slow down or stop. We're just flying by. We take pictures, we get spectra, we take temperature measurements. We're able to measure the gravity by tracking our spacecraft. So we get all the measurements that we can possibly get with a flyby, and it's actually quite a lot. And we're going to learn a lot about our targets from the data that we're able to get. In April 2028, we go to the next one, Lucas. Then a few months after that, we go to the last of the targets in this group of Trojans, which we call the L4 Lagrange point, and that's Orus. Then we dive back in for another close pass by the Earth to redirect it a little bit. And then we come back out, and now we're in these other cloud of Trojans, and that's where we encounter the Patroclus-Menecius binary. And you can see in this little animation on the lower right, sort of a depiction of what the orbit of these two equal mass objects are going around this point in space. All right, well, a little bit about our spacecraft. So it's about the size of a pretty big Mack truck. You can see that most of our spacecraft is those two circular orange things, those are our solar panels, and they're big. And we need really big ones because we will be operating Lucy farther from the sun than any spacecraft so far that uses solar power. So lucky for us, these are a new generation where very large solar arrays can be made and yet be very lightweight. So they open up like a fan, and that's going to be one of the most nail-biting moments for us after launch, because they have to unfurl for us to be able to get power. And until that's done, we're not going to feel very happy. The cone that you can see in the center there, the whole spacecraft is wrapped up with basically looks like aluminum foil. It's called multi-layer insulation, and it's there to protect the parts that are beneath. But that cone is our dish that we use to communicate back to the Earth. That's about 6 feet across. So it gives you a sense of the scale of this spacecraft. Here's a zoom in on the part of the spacecraft where the instruments are. And on the left, you can see a photograph of that with all the instruments on it while the engineers were still working on it before we covered it up with the multi-layer insulation. And on the right, you can see a diagram that shows the same thing, but a little bit easier to see where the different instruments are. We have 3 of them. All of them start with L apostrophe. That just means they're the Lucy version of these instruments. Laurie is our best camera. So we're going to use that for taking pictures and for navigating the spacecraft. LRALPH is our composition measurement instrument. It's a spectrometer and a color imager. And we're using the variation of light as a function of wavelength. So if you think of a rainbow, the variation of those colors tells us what the object is made of. And then LTES is something like an infrared thermometer. So if you've ever had somebody hold up a thermometer to your forehead without touching it and record your temperature, that's what LTES does, but it does it for our asteroid targets. Here's a really nice image when we were still at the assembly location. The spacecraft was built and assembled by Lockheed in Denver, and you can see a test where the solar arrays were being opened. And because they're designed to operate in space in zero gravity, when we test them on Earth, they have to be supported. So that's why you see those looks like marionette strings holding it up, just to make sure that gravity doesn't stress the solar array too much, because it's not designed for working in regular gravity. Here's a diagram of the rocket that we're going to launch on. So it's called an Atlas V. There have been many of these Atlas V launches. And the bottom, you can see the booster, the orange color, that's the first stage. Then there's some adapters, and then we have the second stage that's called a Centaur. And then sitting on the top of that is our spacecraft, and it's in a little shell that's called a fairing. And that's currently standing up in the building next to the pad where everything is being assembled. It's just about complete. We brought the spacecraft from the preparation facility to the pad today. It was put on top of the rocket. Over the next week, there'll be more tests. A few days before launch, we'll fill it up with fuel, and then we'll roll it out to the pad and launch it at 5:30 in the morning. Here's a little animation that shows you this is now just the Centaur second stage after we've launched, and it's going to show you what will happen when we release the fairing, that shell around our spacecraft, and then the spacecraft itself separates from the second stage, and it's getting stuck. Why are we not running? Uh-oh. Sorry about that. Let's see if we can start this again. Oh, well, it's not cooperating. Let's hope that when we do the actual launch, it works a little more smoothly than this.